So we'll begin as oftentimes we do with Bayes' theorem, that the probability distribution, the posterior probability distribution, is equal to the likelihood function multiplied by the prior divided by the marginal probability of the data. And the problem is, in practice, it's very difficult to determine this denominator. But what we can do is, we can just erase it. We can erase it because it's a constant. And then we just have to replace this equal sign with proportional sign. And so the whole idea is that we can arrive at our posterior distribution not directly, but indirectly via a random walk process. And the next 3 videos are going to go over 3 different random walk processes, 1, 2, and 3. The first is a wandering politician. The second is the metropolis algorithm. And finally, Gibbs sampling. And all of these can be thought of as Markov chain Monte Carlo approaches. So we're going to begin with our politician. And so the politician is the ruler or leader of a bunch of islands. And I'm going to number them 1, 2, 3, 4, 5. The politician, however, doesn't know how many islands they've got. But what the politician wants to do is, the politician wants to go on multiple visits to these islands, but the politician wants to visit them such that the frequency of visits is proportional to the population size. Now, in advance, the politician doesn't know what the population size is, but on any one island, the politician can always ask the mayor, and the mayor will tell them what the population size is. So, here's how it's going to work. We're going to start off with what I can think of as initialization. So initially, get this initialization, set the politician on island 2, and in the long run, it isn't really going to matter where the politician starts. And then we're going to keep a running account. These are island numbers, 1, 2, 3, 4, 5, and we're going to tally a 1 here because we've initialized on island 2. So the way this algorithm works is that the first thing the politician does is flip a coin, and if it turns up heads, politician looks right. If it turns up tails, the politician looks left. So let's assume our politician got a tail and looked left. So our politician looks left, like that. So now they look at this island. And what we got to think of is we've got, if he asks the mayor nicely, the mayor will tell what the population size is, and as a consequence, the politician can calculate the population of the current island. And there's the current island right there. And the population of proposed island. There's a proposed island. So the politician is sitting on this island and is wondering whether or not they should move to the other island. And to make that decision, what the politician does is talk to the mayor of each of those islands and calculate this ratio. And actually, I've done this completely wrong, but that's okay. It's good to reinforce the basic idea, and that it's not the population current over proposed. Rather, it's the population proposed divided by population current. So, in this particular case, politician looks left, sees an island with a larger population. So the ratio of population proposed to the population current is greater than 1. And the algorithm says if this ratio is greater than 1, then the politician always moves. So the politician is going to move from island 2 to island 3, and they're going to record that as a tally. And then they're going to repeat the process. They're going to flip the coin, head, look right, tail, look left. So they flip the coin, and again, it's look left. So now what happens is they're looking at island 4. And so they calculate this ratio once again. And now the ratio is less than 1. In fact, let's assume that the ratio of the two populations is equal to 0.8. Then whether or not the politician moves, does the politician move from the new current to the new proposed is proportional to this value here. So to determine whether or not they move, politician just generates, there's a number line, there's 0, there's 1, there's the value 0.8, and they just randomly select a number along this number line, and let's say they selected a 0.6. Well, given a 0.6, given the way this thing is set up, that will enable a politician to know that in fact they should move. Because repeating this process many times would enable a politician to move proportional to this ratio here. So the politician moves from island 3 to island 4, they tally, and then this process is repeated over and over again, where each time to determine the population proposed or population current, and if this ratio is greater than 1, then they move. If it's less than 1, the politician moves with a probability that's proportional to the ratio. Of those two population sizes. And what happens, and what Christie actually shows mathematically, although it's probably not worth looking at the proof, is that if this procedure, this algorithm is repeated a very large number of times, then if we made a histogram, so this is our population size, and let's say here's our 5 islands, 1, 2, 3, 4, 5, then the number of visits is going to increase with the populations, and in fact the number of visits is going to be proportional to the relative population size. So what we have here is kind of a proof of concept or proof of principle. So that we have this politician who doesn't know how many islands. Politician doesn't know in advance what the population size is, but is able to calculate at any one point the population proposed over the population current. And if they do that a very large number of times and use the appropriate algorithm for moving and not moving, then ultimately they're going to be visiting those populations that is in a way that is proportional to the population size. And so, having established this principle, this concept, the next video, what we're going to see is we can expand that concept to apply to theta, where theta is the Bernoulli binomial parameter associated with a binary dependent variable. So that'll be in the next video.